All right, let's talk about something that's probably working away inside whatever device you're using to watch this right now. We're going to break down I2C. If you've ever looked at a circuit board and wondered how all those tiny chips talk to each other without a total bird's nest of wires, well, you're in the right place. We're about to demystify this two-wire wonder.
So let's just start with that fundamental question. Think about your phone, your laptop, even your smart toaster. They are jam-packed with stuff. Sensors, memory chips, little displays, you name it. How in the world do they all stay in sync and talk to each other inside such a tiny space without it looking like a spaghetti disaster?
And the answer, which is kind of mind-blowing when you think about it, often comes down to this simple number: 2. Just 2 wires to connect a whole bunch of different components. It seems almost impossible, right? But that's the elegance behind the protocol we're diving into today.
And yep, those 2 wires are the magic behind I2C, which stands for Inter-Integrated Circuit. It's basically a communication system, a protocol, designed specifically to link up a main brain, like a microcontroller, with all of its little helpers, using just those 2 lines. You could almost call it the secret language our gadgets use to whisper to each other.
Okay, so how on earth does a two-wire system actually manage such a complex conversation? Well, to get it, we need to meet the key players involved. Let's break down the cast of characters, the masters, the slaves, and the lines they all talk on.
So the whole conversation happens on what we call a bus, which is really just these 2 shared wires. The first one is SCL, the serial clock line. The best way to think about this is as the heartbeat of the network. It's a steady pulse that keeps everything in rhythm. The second line is SDA, the serial data line. That's the actual highway where the information, the ones and zeros, travels. And here's a super important detail. Both of these lines are held in a default high state by something called pull-up resistors. This is key because it means any device can pull a line low, but no one can force it high. It's a clever way to prevent electrical fights on the line.
Now on this bus, every device has a very clear role. There's always at least one master, think of it as the director of the movie. It's typically the main microcontroller, and it's in charge. It generates the clock pulse, it starts the conversations, and it ends them. And then you have all the slaves. These are the actors. They're your sensors, your memory chips, your screen controllers. Each one has a unique address, kind of like a phone number, and they just listen quietly until the master calls them by name.
But this whole thing isn't some chaotic free-for-all. Nope. It follows a very strict set of rules, a kind of digital handshake, to make sure every single message gets sent and received perfectly, without any confusion. So let's break down how that actually works.
So let's walk through the most common scenario. A master wants to send some information to a slave. First, the master creates what's called a start condition. This is its way of grabbing the bus and saying, "Okay, everyone, I'm about to talk." Then it broadcasts the unique 7-bit address of the slave it wants to talk to, plus 1 extra bit that says, "Hey, I'm about to write data to you."
And then, the slave that was just called out has to answer back. It does this with an acknowledge signal, or ACK for short, and it's super simple but absolutely vital. The slave just pulls the data line low for a quick moment. It's basically saying, "Yep, got your call, I'm here, and I'm listening." Once the master gets that confirmation, it starts sending its data. And when it's all done, it issues a stop condition to free up the line for the next conversation.
Okay, so that's how a master writes to a slave. That makes sense. But what if the master needs to get information back? Like asking a temperature sensor, "Hey, what's the current reading?" Well, this requires a really clever trick in the protocol.
Okay, stick with me here, because this is where it gets really cool. To read data, the master first starts a conversation and sends the slave's address in write mode. Now that seems weird, right? But it has to do this first to tell the sensor what information it wants, like sending the specific memory address for the temperature reading. Once the slave says, "Okay, got it," the master does something called a repeated start. It basically restarts the communication without ever letting go of the bus. Then it calls the same slave again, but this time in read mode. And that's the cue for the slave to start sending the data back.
And that right there, the repeated start, that's the secret sauce. It's like the master is putting the call on hold to change the subject, but without ever hanging up the phone. This is so important because it guarantees that no other device on the bus can jump in and interrupt this 2-part conversation. It's what makes the whole read process totally reliable.
So we know the how. Now let's talk about the where and the why. Where does I2 really shine out in the real world? Let's look at its performance, its practicality, and the really important trade-offs you have to think about when you choose to use it.
When it comes to performance, speed is obviously a big deal. Now, you can see I2C has a few different speed modes, going all the way up to 3.4 megahertz. But let's be real. For most of the stuff you're going to build, you'll be living in standard or fast mode. That's 100 or 400 kilohertz. They are the trusty, reliable workhorses of the embedded world.
And this really gets to the heart of the whole thing, the big trade-off with I2C. The absolute genius of it is its simplicity. Just 2 wires to connect a whole bunch of devices. It's amazing for saving pins on your microcontroller and space on your circuit board. But, and it's a big but, that simplicity comes at a cost. It's not nearly as fast as other protocols like SPI, and it's really only designed for short-distance communication, like on a single board. It's the perfect choice for nearby, slower-speed jobs, but you wouldn't use it to stream high-def video.
All right, that was a lot to take in, so let's boil it all down to a final cheat sheet. If you only remember 4 things from all of this, make it these 4 key principles.
First up, the hardware. Remember that I2C lines are open drain. All that really means is the device can only ever pull the line low, down to a 0. It can't actively push it high. That's the job of the pull-up resistors. This whole setup is what prevents ugly electrical shorts and allows all those devices to share the lines safely. It's foundational.
Second, the golden rule of timing. The data on the data line, the SDA line, is only considered valid, it only counts when the clock line is high. All the changes, the flipping from 1 to 0, have to happen when the clock is low. This is the core agreement that ensures data gets read correctly every single time.
Third, that handshake, that ACK signal. It's the essential confirmation baked right into the protocol. After every single byte of information, the device that's receiving it has to pull the data line low to say, "Roger that, got your message loud and clear." Without that little confirmation, the whole system would be flying blind.
And finally, our clever little trick, the repeated start. That's the special tool the master uses when it needs to read data. It lets it switch from writing a request to reading a response without ever letting go of the bus, making the whole thing one seamless transaction.
So there you have it, the 2-wire wonder, I2C, broken down. It's simple, it's elegant, and it's the silent workhorse behind countless gadgets we use every single day. And now that you get its strengths and its weaknesses, you're left with the real engineering question. For your next project, knowing what you know now, are you going to reach for I2C or maybe something different like SPI or UART? Because knowing when to use which tool, well, that's the key to great design. Thanks for joining this explainer.